Example 8.8 is going to analyze motion for us that's oscillating using derivatives of sines and cosines, because sines and cosines oscillate. So in this example, we have a weight hanging at the end of a spring from the ceiling. So let's just draw a picture real fast. You've got a ceiling there and a spring hanging from it and some sort of weight right there. So we initially pull down on that spring and we release it. So then it bobs back and forth. And if we were to plot that as a function of time, so my time axis is right there, and this is the height of the weight. So it initially starts down here, and then we release it, and then it goes back and forth as time moves on. Right? And it's given to us by, we actually have the definition there. The height of the function is -5 cosine of t, where I don't think we have any units here. Let's say that this is measured in meters and seconds. So this is going to be 5 meters up. This is going to be -5 meters up, or sorry, I guess -5 meters up makes sense, or 5 meters down. And let's go ahead and locate some points on this graph. This is given to me by the cosine function, sorry, -5 cosine. That's why we start down here at -5 instead of +5. And it's going to oscillate. So we're going to get back down to here at 2 pi. So this value right here is going to be pi, which means we can put pi over 2 right there. And this would be 3 pi over 2, just to give ourselves an idea of what's happening. Right? As you run around that unit circle, at 0, your cosine is maximal. Once you get up to pi over 2, your cosine is 0 right there. And then once you get to positive pi, your cosine again is maximal. And then once you get down here at 3 pi over 2, your cosine is 0. Okay, so the graph looks like that. And let's answer some questions. This first question doesn't have anything to do with calculus. What is the height of the weight when time is equal to pi over 6? So, hey, height function, what are you when time is equal to pi over 6? So at pi over 6, cosine returns a square root 3 over 2. So we have -5 square root 3 over 2. So let's go to our graph and let me switch colors. So here at pi over 6, the height is a -5 square root 3 over 2. All right, B actually brings in the calculus because we need to study how fast the height is changing, or the rate of change of the height. How fast is the weight moving at time is equal to pi over 6? So at the same moment, how fast? What's the slope of that green tangent line over there? So the velocity curve is given to us by the derivative with respect to time of the height function. And if we are going to differentiate -5 cosine t, we get a +5 sine of t. All right, and now we need to evaluate this at pi over 6. So, hey, velocity function, what are you at pi over 6? 5 times the sine of pi over 6 is 5 over 2, or 2.5. This would be measured in meters per second. So at this moment right here, the weight is moving upward at a rate of 2.5 meters per second. All right, C asks, at which time does the weight reach its maximum height? So let's look at that graph right here. Right, that's the height function. That's the -5 cosine t. So at which time values does it reach a maximum height? We're looking for these values here. So we know we're going to get pi out of this. The height function is given by -5 cosine t. And this is maximal when cosine of t is maximal. And these occur at time values of pi plus k pi, where k is some integer. So that just gets all of my maximums. right? It gets this one, but then if I add another pi to it, I end up down here at 2 pi. Or that's not the y value, but the time value of 2 pi gives me another maximum of my height, except it's maximal in the negative direction. So in fact, if I only want to consider the maximums and not the minimums, I should change that to a 2k pi. So now we're only picking up pi and then not 2 pi, but 3 pi. All right, D, when is the weight moving at maximal speed? So this question concerns itself with the maximum of the height function. Now we're going to ask, what's the maximum of the velocity function? Now the velocity function was given to us by positive 5 sine of t. So this is maximal when sine of t is maximal. And this occurs at, so think about your sine curve. Your sine function is maximal at the angle of pi over 2. And if I add k pi to that, then that's going to give me this maximum, pi over 2, and then pi over 2 plus pi would give me that minimum. And for the same reason, if I only want the, oh, actually, it does ask maximal speed, not maximal velocity. So I do want all integer multiples of pi over 2 plus k pi. So if I go back up to this picture here of our height, it's moving fastest at pi over 2 plus k pi. So it's moving fastest at, let's do this in purple. It's moving fastest at pi over 2. So right there at that purple moment, it's moving upwards at maximal speed, because as soon as it passes that moment, the spring starts to be pulled back downwards. And then it's moving maximally here for the same reason. It's moving downwards, but then as soon as it passes that point, the spring starts to pull back up on it. Right, now notice it says speed, not velocity. So that means all of these points, all of these purple points are maximal speed points, because it doesn't matter if it's moving upwards or downwards. If it said velocity, then I would only consider when it was moving upwards.